Hello, everyone. Mr. Sutherland here, continuing our discussion on counting methods. And last time we talked about the fundamental theorem of counting and the idea of a permutation. Today, our focus is going to be on something that's called a combination when counting. And I'll try to explain the difference between that and the permutation. So we'll start with just an example to kind of illustrate the difference between the two. We'll learn the actual formula. The formula is there again for you to be able to use, but your calculator has all the ability in the world to just plug these in and get the value. So here's our situation. Number one, you have 5 Skittles in your hand: cherry, grape, lime, lemon, and orange. If you eat the Skittles one at a time, how many ways can you arrange them to put 3 of those flavors in your mouth? So this time you're eating them one at a time. So the order is going to matter. They're going to be different flavors as you go. So since the order matters, this is going to be a permutation. This is going to be a permutation. We have a total of 5 flavors. We want to pick 3. And if you remember our formula, it's n factorial over n minus r factorial. So that comes out to 5 factorial over 3 factorial. And on our calculator, that's menu, probability, permutation. We're doing 5, and I would say pick 3 of them. So 5 comma 3. And we get that there are 60 different ways that we could do this. Now, what's nice about permutations is, when it's a permutation, these placeholders really work well. So you could really do the work that you see there, or let me move these down just a little bit. We could think, since the order matters, there is a position. The first chance I have 5 choices, then I have 4, then I have 3, and that also comes out to be 60. So that is permutation when order or the position matters. Now, part B, you realize that the order of the candies does not matter. All lime, lemon, and cherry groups represent one combination, meaning they are indistinguishable. How many different flavor combinations can be made by putting 3 Skittle combinations in your mouth at once? So now what this is saying is, let's say we have these 3 Skittles, and we're just going to throw all 3 in our mouth at the same time. So the order doesn't matter anymore. But if we make a list of those 3 things, if we did our permutation list, here, let me move this over to this side, we could see that there are 6 different lists that include cherry, lime, and grape if we were worried about order, if it were a permutation. But the idea of a combination is that each of these groups represents the exact same thing. It doesn't matter when you throw all 3 of them in at once if the cherry enters your mouth first, or the lime, or the grape. They're all the same. And so when order does not matter, that is when we have a combination. So how do we figure out how many combinations there are? Well, first of all, we figure out how many permutations there are. So we do the same thing that we did last time with we had the 5 factorial over the 5 minus 3 factorial, because that's going to list all the groups. And so all these groups are going to be included there. But these groups really don't need to be there, because once these 3 flavors are listed, you don't need to list them anymore. They're repeating. So how do we get rid of repetitions? Well, if you remember about the permutations, like with the word Mississippi, we divide by how many repetitions there are. And then we have 3 things, and we repeat those. So how do we arrange 3 things? It's 3 factorial ways. And so what we're really going to do is this dividing by 3 factorial, that is going to remove the repetitions. So we're removing the repetitions once order does not matter anymore. So really what we have is 5 factorial over 2 factorial times 3 factorial. And I'm going to show you that on the calculator. So I'm going to do control divide. I've got 5. Remember, I get the factorial from this little menu right below enter. 5 factorial over 2 factorial times 3 factorial. And we're getting rid of that repetition, so it should be less. And it is. It's 10, right? We've removed those 6. Every flavor group I come up with that I can remove, they're going to have those repetitions. So here, there are only 10 ways. And this illustrates what a combination is. So a combination is an arrangement of objects. So let's say an arrangement of n objects taken r at a time. So we have r groups where order or position does not matter, right? They don't have a role. They don't have a position. Group 1, 2, 3 is the same as group 3, 2, 1 is the same as group 2, 1, 3. And so this is a combination. So it's n choose r. We have n factorial over n minus r factorial. That should look familiar. That's our permutation formula. And then we have divided by r factorial. And again, really what this here is removing the repetitions because they're listed multiple times, but since the order doesn't matter, we get rid of those groups that are the same. So you're going to use a combination if there's no position or no order given. If there is, like let's say a group and you want to pick a president and a vice president, once they have a position, that's a permutation. No position, no order, it's a combination. So let's look at our first problem. Problem 2, from a group of 40 people, a jury of 12 people is selected. In how many different ways can a jury of 12 people be selected? So in this problem, they're picking a jury of 12. It does not matter who's picked first, who's picked second. So this is going to be a combination. So it's a combination of 40 choose 12. Now again, I'm going to show you the formula written out here, but again, you do not have to do this. 40 minus 12 is 28 factorial times 12 factorial. You could plug into the calculator like this, but what I always tend to do is to go menu, probability, number 3 is my combinations. We're doing 40, choose 12, and we've got a lot of combinations. There's over 5 billion ways that can be selected. So it was 5,586,853,480 different ways. Now, what you cannot do in combinations, the little placeholder method does not work anymore, like we did with permutations, like where I did, I'm going to scroll back up, where I did this method here. That works in permutations because we have an order, first, second, third. So we can use those placeholders. Combination, order doesn't matter. So we're not going to deal with that. We're just going to go straight with the formula. So now, what I would encourage you to do is let's read through problem 3, try it, pause the video, come back and see how you did. All right, number 3 says the Rotary Club has 19 men and 15 women. How many committees of 5 can be chosen so that the representatives are either A, all women, B, all men, C, 2 men and 3 women, or D, 3 men and 2 women? So first of all, we want all the committee to be all women. So that means out of the 15 women, I want 5 of those. Then out of the 19 men, I don't want any. This little part here, that's optional to write. I always like to keep track of everybody that could be used, but anything choose 0 is always going to equal 1. So really all I have to worry about here is the 15 choose 5. And if I put that in the calculator, at 15 choose 5, you come up with 3,003 different committees that would be all women. So using that same idea, the committees that would be all men. So I have out of the 19 men, I want 5. Out of the 15 men, I want 0. So again, this choose 0, you're going to see me put that in the work all the time. But again, I just want to clarify that that part is optional. And really all you need is the 19 choose 5. There should be more committees because there's more men, and there are 11,628. Now, how many different committees can be chosen that have 2 men and 3 women? So here I just keep account of everything. So out of the 19 men, we want 2. And in counting and probability, anytime you see the word and, that is a multiplication. If you see the word or, that is addition. 3 women, so out of the 15, I want 3. So I would just put this in the calculator exactly as we see here. So I would go menu, probability, combinations. I have out of the 19 men, we're choosing 2. Then I'm going to do times. I'm going to go menu, probability, combinations. Out of the 15 women, we're going to choose 3. And press enter. It does all that behind the scenes math for us. So we get 77,805. And for the last one, 3 men and 2 women, very similar. Out of the 19 men, we want 3. Out of the 15 women, we want 2. Multiply that out, you get 101,745 different possible combinations that could be used. So combination, there is no position, there is no order. Doesn't matter. All right, the rest of the problems in these notes deal with, as a lot of probability and counting problems do, deal with playing cards. Now, I've linked this to the assignment sheet, but here is a little cheat sheet for you for playing cards. When we talk about playing cards, there are 52 cards total. Each of these things is called a suit. Like these are the clubs, these are the spades, these are the hearts, and these are the diamonds. And there are 13 of each of these. 4 groups of 13 give you a total of 52. These cards are what are called the face cards, the ones you see a face on, the jacks, kings, and queens. So when problems refer to these are the different things that they're referring to. So I have this link on the assignment sheet so you can go back to it when you need to as you're doing these problems. So the first problem, what I would actually suggest now that I've gone through that is there are, I think, five problems here. Pause this video now. Try all 5 problems. See what you get stuck on after I go through it. See what you can't do, but see what you can do with these 5, and then I will go through each 5 in detail. And now if you need to, once you unpause, you think you got it, you can speed through the video, play me at double time. I'm sure my voice sounds great in double time, and see how you did. So let's start with number 4. From a deck of 52 playing cards, how many 5-card hands can be selected? So 5-card, a hand in a game of cards just really is asking, how many groups of 5 are there? That's all they're asking. Now, the order you get the cards does not matter. Once you get the cards, you can put them in any order you want, but it doesn't matter if you got the 2 of spades first or the ace of diamonds first. You're just given 5 cards. Since the order doesn't matter, this is a combination of 52, choose 5, which comes out to be 2,598,960 different combinations that you could get in any hand of cards. Number 5, from a deck of 52 playing cards, how many 5-card hands, again, how many groups of 5, can have 3 red cards and 2 black cards? So remember, we see that word and again. That's going to mean multiplication. Now here, the order doesn't matter, so it's still a combination. So 3 red cards. So if I go back and look at this, there are 13 hearts and 13 diamonds. So there are 26 cards that are red. So out of those 26 red cards, we want 3 of them to be red. And then that means obviously there are 26 black cards as well. And out of those 26 black cards, we want 2 of those. So this is the combination that's representing the red cards. These are the combinations that are representing the black cards. And this is our keyword and. And if we're to multiply that out, that comes out to be 845,000 different hands. We'll have 3 reds and 2 black cards. Number 6. From a deck of 52 playing cards, how many 5-card hands have 3 eights and a king? Okay, so we have 3 eights and a king. Well, if I go back to my list, if I look at my eights, there are 4 eights. We want 3 of them. So I'm going to do that first. So out of the 4 eights, we want 3 of them. Now, we also want a king. There are 4 kings. Out of the 4 kings, we want 1 of those. Now, here's the mistake people make. They stop here. But right now, I've picked 3 eights and 1 king. I only have 4 cards. I need 5. So that last card can't be an 8, can't be a king. Otherwise, these things are mistaken. So I had 52. If I take away those 4, I have 48. If I take away those 4, I have 44. There are 44 cards left in the deck that aren't an 8 or a king, and I want 1 of those. That's like the hidden card in there that we have to make sure we keep a track of. So now we can calculate that. So I've got, for this one, I've got 4, choose 3. Then I've got, for the next one, we've got 4, choose 1. Out of the 4 kings, we want 1. And then at the end, out of the 44 that are left, we want 1 of those, which 44 choose 1 is just going to be 44. And that comes out to be 704 different hands have that combination of cards. And this is how they're going to get probabilities for games of poker. And we're going to talk about probability coming up in a couple classes. Number 7, from a deck of 52 playing cards, how many 5-card hands are all 5 cards of the same suit? Well, that means all the cards could be hearts, or all of them could be spades, or all diamonds, or all clubs. So we could have all of the cards be hearts. You're going to get my great drawings here. All of the cards be diamonds. Yeah, that's a diamond. Or all the cards be the spade, the club. We'll do, I have no idea what that is. We'll go with a club. Or all of them could be spades. Yeah, that's it's embarrassing, this kind of artwork here. So we're just going to we'll just try a little better. Yeah, that's clearly much better. Much better. So what's the probability, or how many combinations are they all hearts? Well, that means out of the 13 hearts, I want 5 of them. Now, I'm going to erase this and move this over a little bit. What I could add then is out of the 39 other cards, I don't want any of those. Again, this is that optional piece that I talked about earlier. Also now, in math, when we have or in probability, that's a plus. Or they all could be diamonds. So I could have 13 choose 5. Or they all could be clubs. So 13 choose 5. Or they all could be spades. Now from the beginning, what you could notice is I could have just done 4, because there's 4 suits, times 13 choose 5. And that comes out to be 5,148. All right, the last one. From a standard deck of cards, find the possible number of 5-card hands that contain at least 3 hearts. So that means we want at least 3 hearts. So we need to find the number of hands that have 3 hearts, or 4 hearts, or 5 hearts. So 3 hearts, that means out of the 13 hearts, we want 3. But we need 5 cards altogether, so that means out of the remaining 39, we need 2. Or, so that's a plus. 4 hearts means out of the 13 hearts, we want 4. Out of the 39 remaining, we want 1. Or if all 5 are hearts, we've actually kind of done that already. Again, this piece at the end is this part's the optional. You multiply your combinations and add them together. you get 241,098 possible hands. So the main thing I want you to take away from today is that when we talk about a combination is an arrangement of objects in which the order or position does not matter. And so the formula is a little different, but the approach to the problems is similar. I hope you find this helpful. If you have any questions, feel free to email me, and I'll be happy to set up a time to talk to you to help walk you through some of the problems if you're struggling with the homework. Take care. Talk to you guys again soon.